rational functions. What are rational functions? Fractions. Rational, the root there is ratio. Ratios are fractions. Rational numbers are fractions. Rational functions are fractions, but they're polynomial fractions. So all of the polynomial stuff that we spent the last 3 weeks or whatever talking about, if you take two polynomials and add them together, you get another polynomial. If you subtract them, you get another polynomial. If you multiply them, you get another polynomial, right? Like think about, multiplying, I don't know, x plus 1 times x plus 2 or something. That's one polynomial times another one. It gives you a different one, right? So there's nothing like new or interesting to talk about with addition, subtraction, or multiplication. You just get another polynomial that, follows polynomial rules. Division, though, as usual, is different. So rational functions are things that look like this, and don't worry about, writing the like P's and Q's or whatever, but where these things are both some kind of polynomial, right? So where you divide one polynomial over another. We talked about function division like a while ago. The same stuff still applies here, but in particular, one thing that comes up is that because we're dividing, we run into stuff we need to be careful about if the thing that we're dividing by is 0, right? So one thing that we know how to do really well at this point, or hopefully know how to do really well at this point, is find zeros of polynomials, right? If a rational function is a fraction, let me write like an actual example to sort of point at instead of just an abstract thing. Let's say, just as an example, x plus 1 over x squared plus 5x plus 6 or something. That, the numerator, I know everything I need to know about, right? It's a linear function. It's got slope 1. It's got y-intercept 1. I can find its zeros if I need to. That thing is quadratic. And what do we know about quadratics? Right. Okay. So I can figure out everything I need to know about that. What we're talking about now is, okay, what happens if I, make a quotient, make a fraction out of those two things? What changes? The most significant thing that changes, and the thing that we're going to spend kind of the majority of our time talking about, is that sometimes this is 0. And if it's 0, then we end up with something where I've got, something, who cares, divided by 0, which is undefined, right? So that's the thing that we're going to need to spend kind of most of our energy figuring out how to deal with. Okay? Just as sort of a starting point. All right, so in the intro video thing, we looked at 1 over x. We'll just kind of pick up back there. And let's just look at the graph. There it is. So what's the first thing that jumps out at you? It's not connected. Yeah, it's not continuous. If I'm going to draw that thing, I have to draw it in 2 separate pieces, right? I have to lift my pencil at some point. Mathematically, that means it's not continuous because there's this sort of, jump or gap, right? If I think about this, in the kind of the same way as we did polynomial stuff and like it's a roller coaster track, this part's fine, this part's fine, things are going to get rough, right? So what happens here, if we want to describe this, is as x approaches 0 from the left-hand side, the function is pointing down toward negative infinity, right? On the other hand, if I approach x from the right-hand side, or if I approach 0 from the right-hand side, the y values are pointing up toward positive infinity. Okay, so real quick, and again, this is just recapping, stuff that was in the video, but coming off a break, so we'll start slow. What's the domain of this? Everything except 0. Can we explain why the domain is everything except 0? I for sure can't plug in x equals 0, right? F of 0 would be 1, divided by 0, division by 0 is undefined, right? Always. We can't divide by 0, so 0 definitely doesn't work. Is everything else okay, though? Yeah. You give me some negative number, I can plug it into that. I get 1 over whatever I plugged in, that's just the reciprocal, right? Sometimes this is even called the reciprocal function because that's what it does. -5, for example, plug in, I get 1 over -5, so -1/5, -0.2, whatever. Like, that's fine, right? I get some value for it. Negative numbers are okay. Positive numbers are okay. If I plug in some messy, decimal or fraction or whatever, I just get 1 over 1/4, which means you take the reciprocal and you get 4, and that's fine, right? Okay, just some number. That's all we're looking for. The only thing that would be a problem then is 0 itself. That's the way you interpret this. Everything except x equals 0, right? X because it's domain. This is from forever on the left up to, but not including 0. Union because we're picking up a disjoint thing. Everything beyond, but not including 0 to forever to the right. And so it's everything except for that one value. So if we think about kind of the big picture thing, and that rational functions are things that look kind of like this, how many zeros does this thing in the denominator have? 2. So how many places would this function as a whole be undefined then? Whatever the zeros of the denominator are. So when I figure out the domain for this, which we'll do in a minute, I would have 2 things that I sort of need to skip around, which means the domain would be in like 3 disjoint. So we're going to see a lot of stuff like this when we talk about domain for these functions. Okay, back to the graph. How about the range? Same thing. We're talking about y values now, so we're looking at it sideways, but if I look at the graph sideways, it looks a whole lot like if I look at it straight on. The reasoning for that is a little less direct, but we're talking about y values now, so we're talking about solutions to that equation, right? Is there any way I could solve this? 1 over x equals 0. I would either need to take the reciprocal here, which means I take the reciprocal there, and I get 1 over 0, and that's a problem. Or I could think about, getting rid of the fraction by multiplying, but then I get 1 equals 0, and that's a contradiction, right? So this has no solutions. There's no way to make that true, which is why I have to leave out y equals 0, because I can't get there, right? Another way to think about it, if you give me a positive number to plug into this, what's the result going to be? Positive, right? If you give me a negative number, the result's going to be negative. And I can't plug in 0 because 0 would be undefined. So there's no way that this thing is ever going to cross the x-axis either. This, by the way, means that this has no y-intercept and no x-intercept either, right? Because we leave out 0 from both the domain and the range. And what happens at y equals 0 and x equals 0? We get asymptotes. What are asymptotes? Yeah, they're lines that kind of fit into the gaps. So at x equals 0 and at y equals 0, there are these lines that aren't really part of the function. That's why I drew them in a different color, but they show me what the function does. The idea is that the further out I go, let me do it this way. Okay, maybe I can't. The further out I go, the more and more the function starts to look like that line without ever actually quite getting there. Right? It's sort of gradually squeezing in toward that line, but never reaches or crosses it. If I zoom this thing way out, I almost can't tell the difference between the function and this, you know, cross-shaped thing that's made by the straight line. It's just this little curvy bit in here. If I look at kind of the big picture, that's what asymptotes are. They're lines that, you know, give you a guide sort of for what the thing does. I think I'm like a scaffold kind of for drawing the thing. This has a vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. Vertical lines look like x equals wherever they are. Horizontal lines look like y equals, again, wherever they are. Again, we talked about this a little bit last section, unit, whatever, about, you know, equations of lines and making sure we're clear about when something is a point versus when it's a number versus when it's a line. Again, you should be really clear about that. Asymptotes are lines. That means we write them as equations of lines. So the x equals or y equals part is important. Okay. Everybody good so far?
Wait, sorry. So why is it at x0 and y0?
So y equals 0, y-axis, right?
Yeah.
Y equals 0 is all the points that sit on the x-axis.
Okay.
So that's saying that there's a horizontal asymptote at y equals 0. That's describing this line that as I look at the ends of the graph, that way, show me what the graph does, basically.
So we won't really have to say where the asymptote starts, just on what.
Yeah, so the asymptotes don't describe what's going on in the middle here.
Yeah.
They describe what's going on at the ends. So
Okay.
asymptotes are basically our new way of talking about end behavior. For a lot of rational functions, some of them, the ends can be pointing, you know, up or down or whatever, but a lot of them we're going to see the ends are basically going to level off. And when they level off, that's what a horizontal asymptote is, right? So if you just kind of ignore this stuff in the middle and look at the ends here, and, you know, even just thinking about like using arrows to describe it, you would have one pointing that way and one pointing that way, right?
Okay.
So, you know, level, that's what I mean by that, which means that there's a horizontal line that shows me what the thing does. Okay, is everybody else okay with that? And the vertical asymptote does the same thing, but up and down. So it's not describing what's going on here, it's describing what's going on, you know, at sort of the point and stick, the top of the graph and the bottom of the graph, that it's, you know, squeezing in on that line, but not crossing. Yep. Okay. Anything else so far? Yes. Yeah, they can be at different places, and that's one of the things that we're going to be working on, you know, today and maybe into tomorrow is figuring out like, okay, how do we locate these things, right? The way that you know, sketch a graph if we wanted to, or sort of analyze or break down a rational function, a lot of times is going to come down to the stuff that we can sort of pick out easily, right? Like we would with polynomials. The stuff we can pick out easily there, like on the, you know, the graphing problem on the test that I say in the back. The stuff we can pick out easily is the zeros and their multiplicities and the end behavior. Well, now we're talking about taking two polynomials and dividing one by the other, but we can still pick out things like zeros easily. And what do those tell us? What does the, you know, end behavior thing mean now when we take two of them and put them together? What does that tell us? So a lot of this stuff is going to kind of overlap with things that we've been doing. We'll be using a lot of the same skills to figure out what's going on with these. Okay. And then once we locate where things, like if I wanted to, you know, sort of build this thing up from scratch, what I would do first is figure out those asymptotes and, you know, sort of draw those in, because then I've got like a framework for what the function does, right? I get the asymptotes and then I go, okay, well, the rest of it sort of squeezes in to those, and maybe we find a few points and stuff along the way too. Okay? All right, so we will come back to this one that I just made up, or actually we'll do this one that's very similar. But let's start with that. So 1A here. Start with that, take a look at the graph, think about the domain, the range, the x and y intercepts, the asymptotes, all that stuff. Think about like where it comes from graphically, looking at it that way, and then also maybe why things might be happening the way that they are.
The answer would be, but I don't know how I get back in. She saw which would speak. Well, I think it.
What the other point?
Add two. To get 1/2, 1/x equals 2. And you divide that by 5 or multiply by 9.
So,
And where, looks like an exit goes from a zero.
Yeah, mine doesn't, I don't know, it's supposed to.
Zoom. I had to zoom mine, I used Desmond, but I had to zoom mine in. If you zoom it out, it looks like it touches the one. It did earlier.
Yeah, mine doesn't look like that at all.
Okay. If you didn't know this, if you press alpha Y,
Wait, how did you do that?
you can put it in as a fraction.
Oh, that's probably it. Alpha Y.
Alpha, like you did at the table, alpha Y, and then the first option
Okay. Alpha Y.
at the top left.
Yeah.
No, it's the Y equals that plot. There.
Oh, alpha.
Oh, and then,
I didn't know that. Okay, so the first option, just
Alright.
like hit it or.
Oh, there we go. That's probably.
The other way to do that would be to just throw a set of parentheses around the x minus 2. Like when
Okay,
you-
so I
when you
can-
type it
I
in.
can just do the division.
Just, yeah, because what it was doing, the way you had it,
Yeah.
is 1/x, then minus 2, which is why it looked like a different thing
Yeah.
than that.
Yeah.
Yeah, so if you're getting a weird thing from a calculator, it might be, that you need to throw parentheses around it, or you need to make sure that x minus 2 is the denominator. Set of parentheses would do that. I didn't know about that enter it as a fraction thing. That's cool. Okay.
Watch the thing.
Okay.
Down here where it says real, change it to AB plus BI.
Yeah.
So if you do negative 16, don't say right, like that.
Do the same thing. So, where does it look like in? So, kind of be. Anywhere that is. Fine. Here, where there's this sort of geometry, right? That's what's.
Oh, brain dead. You get the line, so you split them zero. So it'd be 1 over 0 minus 2.
Right. Yeah. Which, for similar reasons. Because, no matter what. The thing like they're taking from because when it's 0. Or, skipping over. Get next to 2, the 2 minus 2, 2, 3. So, anything more than us, either gonna be positive or negative. Which means that this is a fraction, but they mean positive or negative. So that's why this drag, so sideways from my perspective, kind of breaks around and goes across the x axis. Because you don't have it for yourself. And y equals 0 is not so linear.
That's where it's not this.
So asymptotes are the ones that are.
So it really doesn't have an x-intercept.
Yep.
But when I solved for it, I still would get 2 correct, so I would add 2 here, and then multiply by 1, so I'd get positive 2.
X-intercept means you're setting y to be 0.
Yes, sir.
If you try to solve this, you gotta treat this like it's all one thing.
Okay.
So the ways you could do this would be to either think about this as like a fraction that you want to get rid of and multiply by the denominator. So that those cancel. But then when you multiply over here, it just sort of disappears because you're multiplying by 0, right? And you end up with one equals 0. which is a contradiction. Or you take the reciprocals of both sides, you get x minus 2 over 1 equals 1 over 0, which is also a problem. Yeah. So that's why there's no way to make that work. Another way to think about it is an equation like that is only going to be true. You're asking where a fraction is 0. That's only true if the numerator is 0. And that's not 0, right? Yeah. Okay, so there's the graph of 1 over x minus 2. What's its domain? Everything except 2. How do we know the domain is that's not a 2, that's a, there we go. How do we know the domain is everything except for 2? Okay, if I look at the graph, it looks like there's a vertical asymptote at 2, right? A little bit harder to tell on the calculator screen, a little bit easier to see on Desmos maybe, especially if you make it show you every value instead of skipping the 5s or whatever. But yeah, I mean, this thing looks like it sort of splits around x equals 2, right? It looks like that's where this break or, invisible wall, if you want to think about it that way, it looks like that's where that happens. How else could we tell that x equals 2 is going to be a problem? If I take the denominator and set it equal to 0, what do we get? X equals 2. That means if I try to plug 2 into the function, I'm going to get something with 0 in the denominator, and division by 0 is undefined. Always, right? You can't do division by 0. So the zeros of the denominator correspond to places where the rational function, the fraction, would be undefined. And undefined literally means places that are not in the domain, right? The domain is all the places where it is defined. Places where it's not defined then shouldn't be in the domain, right? So the one and only time this would be undefined is 2. So the only thing that we need to skip over or leave out or omit from the domain is x equals 2. And this time you union around it and use open intervals. Okay. Okay, so x can't be 2. And what did we learn about x equals 2? From the graph, I think, Sabrina, I think you led with this, or someone did. That there's a vertical asymptote there. Just by, inspection visually, right? I see that there's a vertical line there that the graph is sort of, breaking around, right? That's a vertical asymptote. Okay, you pretty good with that? What about the range? Looks like everything except 0, right? If we were going to describe, oh, right, I can't use the laser pointer on that side. If we were going to describe the graph or the end behavior of this, all right, if I said, hey, ignore the middle, tell me about the end behavior, just like for polynomial stuff, what happens that way and what happens that way, how would you describe the ends of this thing? Choices are, pointing up or down or sort of in the middle somewhere, like leveling off. It's level, right? The ends go, straight out to the sides. Where? Along the x-axis. Okay. Well, when we see something like that, that's a horizontal asymptote. This one's at y equals 0. And what it looks like is happening is that one side is sitting just above and the other side is sitting just below that line. And you can, fiddle around with the graph all day if you want, move out that way. This is always going to be sort of just underneath. If you zoom in far enough, you can see a little gap between them, right? Like it never actually crosses. There'll be more coming about this. So basically, yes, but there are also a couple of things that we need to, think about. The other way that we can, sort of get this, and it's kind of tied into the intercept idea as well, is that if I try to solve 1 over x minus 2 equals 0, like I'm finding x-intercepts, my choices here, what happened to my 0? My choices here would be to either take reciprocals of both sides or multiply the fraction out so that those cancel. But then I'm left with something like 1 equals 0, which is a contradiction, right? There's no variable there. There's nothing to change. It just says, hey, 1's got to be 0 and 1's not 0. So that's another reason why the range does not include 0. There's also no x-intercepts then, because the range doesn't include 0, and that's what x-intercept does. Okay, only other thing would be the y-intercept. How do you find a y-intercept? Plug in x equals 0. So g of 0 would be 1 over 0 minus 2, which is negative 1/2. So the y-intercept is 0, negative 1/2. Okay. Just to also tie this back to other stuff that we know. How does 1 over x minus 2 compare to 1 over x? The only thing that's different is this minus 2 that's happening. Yeah. Which way? The minus 2 directly to x, right, on the inside of what the function does, which means the denominator here. It's the same function, but shifted 2 to the right. There's 1 over x in black, and then 1 over x minus 2 in purple there. It's the same function, but shifted 2 to the right. So all the same stuff happens, but shifted over. Okay. Questions so far? All right, let's kind of recap a little bit and make maybe like a list of things. Stuff we need to know. Where would the denominator equal 0? That's probably first and foremost thing that we should think about when we look at one of these. Anytime you deal with a function, an important thing to know is, hey, when does that function actually exist, right? When does it make sense to use that? We haven't run into a lot of that so far because we've mostly been talking about things that are defined everywhere, like polynomials, right? Last chapter, if I asked you about domain, it was automatic, right? It's negative infinity to infinity. It's defined everywhere because that's how polynomials work. That's not true anymore. So that's the first thing we want to think about is what does the domain look like? Well, the domain looks like everything except where the denominator would be. So identify those, throw them out. Domains are going to look, something like this then, where we sort of omit a few things. That tells us about domain. It also helps inform us about vertical asymptotes because those are the places where we have discontinuities. It might even help us with things like y-intercept. If we figure out from the domain that it never crosses the y-axis, that tells me that there's no y-intercept to go looking for. Okay. The other thing that we want to think about is the in behavior. And again, you should kind of notice some overlap with the polynomial stuff, right? That's one of the big things that we did there right off the bat usually would be, hey, what do the ends look like here, right? We can do the same thing here. In behavior, and if there are any horizontal asymptotes. So let's think a little more about, how this in behavior thing works. This one, we just, both of them that we've done so far, we just looked at a graph and noticed, hey, this looks like it's kind of leveling off If I look at the left and right hand sides of this and ignore the stuff in the middle, those look like they're leveling off. Let's see if we can figure out why. So this same function, 1 over x minus 2, what did we look at to figure out in behavior for polynomials? The degree, the leading term, right? The degree, whether that was even or odd, told me about whether the ends go the same direction or opposite ways. And then the coefficient on the leading term told me about whether it was, pointing up or down, right? Okay, well, if we look at this thing and I say, hey, think about this the same way, right? What's different? And maybe it might be easier to see, pointing at something like this. What's different if I say, hey, look at this and think about, leading term or degree or in behavior? Do it. Is it? Degree means the largest power, right? The thing that's different is that there's kind of a leading term in both the top and the bottom, right? It's not a polynomial, it's a fraction with a polynomial in the top and the bottom. So if we talk about leading terms, there's kind of two, right? There's the top and the bottom. The same thing's true here. It's just that the leading term on top is just 1, right? Because it's degree 0. Well, what we do is take the leading terms, one over x, and then all that degree and in behavior stuff really comes down to what happens when x is a really big number. What does this do if x is a really big number? It's really, really small, right? If x is 10 bajillion, 1 divided by 10 bajillion is, I don't know, 0.00000001 or something, right? It's some really small, but still positive value, right? So going that way to the right in the direction of positive infinity for the x values, I get small positive numbers. Going that way to the left in the direction of negative infinity for x values, I get small negative numbers, right? If x is negative 10 bajillion, I get, well, the reciprocal of that's a small negative number. So what happens is that this goes to 0 as x goes to either infinity. And what that really says, think about doing the like in behavior stuff. The, x goes to infinity and y goes to here, stuff that we maybe didn't like so much, but hopefully got the hang of eventually. To the left or to the right, function or y values go to 0. That's saying they're approaching the x-axis, right? This is saying this thing levels off, and where it levels off is 0. That means that it's got a horizontal asymptote at y equals 0. So now we can kind of see the horizontal asymptote coming rather than needing to, rely on just the graph to figure out exactly where it is. And that'll be important for some stuff coming up. Okay. So that's kind of how we think through in behavior. We're going to do another example. So nobody panic. Let's look at this function. And before we graph it this time, let's think about the domain. What do I need to figure out to know what the domain is for this function? Any place that it would not be defined, right? Any place that it would not exist, which is going to be anytime the denominator is 0. That's enough. I'm just kidding. You do have a quota, but for the domain, we need to figure out where the denominator would be 0. Okay, we'll take the denominator aside, x squared minus 5x minus 6, set it equal to 0. Oh, hey, it's a quadratic to solve. Good thing we know so much about solving quadratics, right? When is that 0? This one factors, or you can use quadratic formula, solve it somehow. Yeah. Okay, what does that mean? If I let x be 6 or -1 and try to plug that into the function, I'm going to get, let's say x equals 6, for example. H of 6 would be 6 plus 3 over 6 squared minus 5 times 6 minus 6. That's 9 divided by 0, which is still bad news, right? That's still undefined. A similar thing happens at 1 or -1. What's the domain then? Everything except those 2 points. Anything else in the whole universe works just fine. But these 2 values, which are the only x values where this denominator would be 0, are going to be undefined. So how do I write the domain then if it's everything except for these? Well, start with everything. But then we need to leave some stuff out. We need to leave out -1. So I go up to -1, but then skip over it. And that's how you skip over something, right? That's erasing a single point. If you like drew this on a number line, I would just like put an open circle around -1, right? And then skip over 6 also. I can't believe I actually spaced that right the first try. That's kind of a miracle. Well, maybe don't appreciate that, but that's what the domain would look like for this, because it's everything except these 2 places where bad stuff happens. If we looked at the graph, we would see what happens there. Let's do that real quick. Y equal, that's not an equals, neither is that. Okay, just keep mashing buttons until it works. There we go. Over x squared minus 5x minus 6. What do you see at -1 and at 6? Vertical asymptotes, right? The graph looks, wackier. Now it's in 3 pieces instead of 2, but at -1 and at 6, I see this kind of break in the graph where, the thing is sort of approaching on both sides. So we've also learned that there are vertical asymptotes at x equals -1 and x equals 6. Okay, we will pick up there tomorrow. Give the rest of that problem a shot, like try to finish that, and we'll pick up there tomorrow. Okay? All right. You have a good day. I'll see you then. Oh, I didn't know that. Yes.